Let's talk about calculating the molar mass of a gas from the density of the gas. You can either determine the molar mass of a gas given PVT and the density, or you can calculate the density from the molar mass, again given the pressure, volume, and temperature. As you know, the equation that governs this type of calculation is PV equals nRT. I won't bother you with the song. P is pressure. It's measured in kilopascals or atmospheres, sometimes in torr or millimeters of mercury. V is the volume, and we measure it either in liters or milliliters. N is the number of moles, which goes along with liters, or millimoles, which goes along with milliliters. R is the gas law constant. That's, generally speaking, either 8.314 joules per mole Kelvin, which is the same as 8.314 kilopascal liters per mole Kelvin, or 0.0821 liter atmospheres per mole Kelvin. You determine the R that you use from the units that you will see in the atmospheres or kPa. So the pressure unit determines which of these two R's you will use. And of course, T stands for the absolute temperature in Kelvin, which you'll recall is the Celsius temperature plus 273.16. Now there is an alternate equation for the molar mass as a function of density. We derive it in this way. We start with PV equals nRT. Now we know that N, the number of moles, is the mass of whatever it is we're measuring divided by the molar mass of that particular substance. Thus, we can change the original equation by substituting mass over molar mass for N and dividing both sides of the equation by the volume, V. We get pressure equal to the mass of the substance times RT divided by the product of molar mass and volume. If we change this into mRT over V times the molecular mass, we see that the mass over the volume is the first term, and that's the density at that particular temperature and pressure. The molar mass then can be shown to be equal to the density times RT over the pressure. You can talk to your teacher to find a mnemonic so that you can remember this equation more easily. This is exercise 5.14 from one of the textbooks that we refer to. So we ask the question, what is the molar mass of a gas if its density is 1.95 grams per liter at 1.50 atmospheres and 27 degrees Celsius? If you'd like to practice this, you can turn off the video and then come back and see how it's solved. The molecular mass, of course, is dRT divided by the pressure. We plug those numbers in. The density, notice I wrote grams in the numerator and liters in the denominator, is 1.95 grams per 1 liter, multiplied by R, and since we're measuring the pressure in atmospheres, we use 0.0821 liter atmospheres per mole Kelvin. Mole Kelvin goes in the denominator. And finally, on the numerator, we multiply by 300 Kelvin. In the denominator, we have the 1 liter from the density, and we have 1.50 atmospheres, which is the given pressure. We come up with 32.0 grams per mole when we do the math. Now, for a kind of a college question, something you might see like this would be on the AP exam. Let's suppose you have an evacuated flask that has a mass of 134.567 grams. We fill it with an unknown gas, and the pressure is 0.9671 atmospheres at 31 degrees Celsius. We then find the mass of the gas plus the flask, and it's 137.456 grams. We then take all the gas out of the flask and fill it with water. And at the same temperature, the mass is 1,067.9 grams when the density is 0.997 grams per milliliter. And of course, we can find the molar mass of this gas. Here's how we set it up. We need the gas density, absolute temperature, and pressure. The mass we can get by simple subtraction. The volume now takes the use of the mass of the water and the density. The temperature, of course, is 31 degrees Celsius plus the conversion factor. And now we can solve the problem. We find the mass of the gas from subtraction, 2.889 grams. The volume of the gas, which requires the water mass alone, we take the mass away of the flask, and we get 933.3 grams. We divide by the density of water at that temperature, and we get 0.9361 liters. So the density is the mass of the gas, 2.889 grams, divided by the density we just calculated. The density is 3.086 grams per liter. The temperature is 304.1 Kelvin. And now we take those numbers, plug it into our mm equals dRT over pressure, and we find this is the setup of the numbers. Again, we write the grams in the numerator and liters in the denominator. We'll see that all of the liters cancel out. The atmospheres over atmospheres is also 1. Kelvin over Kelvin is 1. And the only units we have left over are grams in the numerator and moles in the denominator, grams per mole. The answer is 79.63 grams per mole once we do the math. You can also do these problems with the Dumas method. Dumas was a 19th century chemist. He was the Karlsruhe chairman, that great conference in mid-century. And he developed this method for finding the molecular mass of a liquid. And what you do, as long as the liquid will boil at a temperature below 100 degrees, you simply put the liquid in the flask, find its mass, and put it in boiling water. That will vaporize all of the liquid and leave the gas. You then close up the flask and find the mass of the flask with the gas inside. Once you have the mass of the gas inside, you know the density of the gas, you know the temperature of the boiling water, you know that atmospheric pressure was present before you sealed up the flask. And so you know PV, and you know the temperature, so you can figure out from the density the molecular mass. You can do this in your own way. Now, the last thing you need to be aware of is how to find the density of some gas that you know the formula for. And we're going to do this at STP, although you could do it at any temperature and pressure. Now, you may recall that when you have the molecular formula of anything like this, you can simply add up the atomic masses to get the molecular mass. And so if you look at carbon, there's 3 of them. 3 times 12 is 36, and the hydrogen 1 times 8 is 8. When you add those together, you get 44, which is the molecular mass. Now, you may recall that the volume of 1 mole of any gas at STP, standard temperature and pressure, 0 degrees, 1 atmosphere, is 22.4 liters. So you have the mass of a mole, you multiply that by the volume, inverse of the volume of the mole, 22.4 liters goes in the denominator, and you can get the density of anything thing that you know the molecular mass of, as long as it's a gas, at standard temperature and pressure.